Hello, we're back for Unit 9, Day 2 Notes, Part 2. All right, so we are on this page now where I need to define a bunch of line segments. So there's something called a tangent to a circle. Now, it's different from tangent in trigonometry. So a tangent to a circle is a line that touches a circle in exactly one point. It starts outside the circle and touches the circle once. So if we go down here to name the following, can you name a tangent? So look for a line segment that starts outside the circle. So it's going to start here at D and touches the circle once. So line segment DC is a tangent. All right, tangent's very important to understand and know. A secant of a circle is a line that intersects a circle in 2 points. So it starts outside the circle. I should probably add that in. Starts outside for a tangent. Same for a secant. Starts outside. And it touches the circle twice. So can you name a secant? So look for a line outside the circle and it touches twice. So line segment DA starts at D, hits B at B, and then hits again at A. All right, a chord of a circle is a line segment whose endpoints are on the circle. It's completely inside the circle. So in this picture, there are 3 chords. So the segments that are inside the circle, line segment CA, line segment AB, and line segment BC are all chords. All right, now there's something I would like you to do. So in this space kind of right over here, draw a circle. O. All right, so I'm going to draw a circle, and I'm going to put the center in and call it O. Step 2, draw a tangent to circle O. So a tangent is a line segment that starts outside the circle, anywhere you want, starts outside the circle and touches the circle once. All right, it can be a ray, it can keep going, it could stop here, it doesn't matter. Label the point of tangency P. So where that tangent touches your circle in one spot, label that P. Draw a radius OP. Now what can you say about the radius and the tangent? And the conclusion is they are perpendicular. So this leads to a theorem. A line tangent to a circle is perpendicular to the radius at the point of tangency. It is something you're going to have to look for. All you're going to be told is that a tangent has been drawn to the circle. So you need to look for a tangent attached to a radius. Now it could also be attached to a diameter. So it doesn't matter if it says radius or diameter. As we know, a radius is half the diameter. So it makes a right angle. So again, you're going to get 90-degree measurement right here, but without being told that. So it's something you need to look for and recognize. All right, now do you see how this angle is partly inside the circle and it's partly outside the circle? That kind of angle acts like an inscribed angle. So it leads to this down here. The measure of an angle formed by a tangent, here's a tangent, it's outside, touching the circle once, and a chord. So anytime you have a tangent and a chord, it acts like an inscribed angle. It's going to be half, the angle is going to be half of its arc. So if I extend this, it creates arc BC, and the measure of this angle here, the measure of angle C, is going to be half the measure of that arc. So let's say this arc was 100 degrees, that angle is going to be half. It's going to act like an inscribed angle. Same in this picture. It works for this is a minor arc. It also works for a major arc. If you have a tangent and a chord, you get that angle that's kind of partly in the circle, partly outside. It acts like an inscribed angle to its arc. So if this arc was, I don't know, 200, the angle is going to be 100. It will be half. So that is something you are also going to have to look for. It acts just like an inscribed angle. Okay? So you need to recognize that. I don't really care if you understand the theorem or know the theorem. You just have to understand that it acts like an inscribed angle. All right, let's flip and do some examples. All right, in the diagram to the right, ray KJ is tangent to the circle at point J. Find the values of x and y. All right, so y, it looks like this angle, angle QLJ, and angle x, they want is really angle KJL. And all we have is 35 degrees. So I'm going to start with that, 35 degrees. I'm going to follow it out. It hits the circle at arc JL. And that's an inscribed angle. So arc JL is going to be 2 times 35. It's going to be 70 degrees. Now, if you look at this angle that's labeled as X, it's made of a chord and a tangent. It is half inside the circle. Oh, it's not half. It's partly inside the circle and partially out. It acts like an inscribed angle. The vertex is on the circle. So X degrees is going to be the arc divided by 2. So X is going to be 35 degrees. All right. I don't know if I could squeeze it in there, so I'll just put it here. All right, now we have to find the measure of angle Y. Do you notice? Here is the center of the circle. This is a diameter. Diameter, we end up with 180 degrees from arc Q to L. 180 degrees, but that much of it is 110. So arc QJ, arc QJ is 180 degrees minus the 70 degrees. It's 110 degrees. And angle Y, if you zoom it out, it intercepts that arc. So Y is going to be your arc divided by 2. It's an inscribed angle. So Y is going to be 55 degrees. All right, there's another theorem, another relationship you got to look for and notice. All right, think about you're given parallel lines. Now remember, parallel lines are always the same distance away from each other. So think about the arcs that are created by these parallel lines. It creates arc AC and arc BD. What do you think is true about them? I'm hoping you said they are congruent. They are. We can put congruent tick marks on arcs just like we do segments. So if you are given parallel lines inside a circle, it creates parallel arcs between the two parallel lines. Okay, in a circle, if chords are parallel, then they intercept congruent arcs. So that's a theorem, or you can just kind of think about it, and hopefully it makes sense. All right, last example. Given line segment AB is parallel to line segment CD. Parallel. Find the measure of arc BD. In the picture, we are given 20 degrees. Angle B is 20. So I'm going to start with that. If I zoom it out, it hits arc AC. That's an inscribed angle. So arc AC is going to be 2 times 20 degrees or 40 degrees. All right, now you can apply the theorem we just used. If you have parallel lines, it creates congruent arcs. So arc BD would also have to be 40 degrees. Or if you notice parallel lines cut by a transversal, here's the letter Z. You're going to get alternate interior angles are congruent. And then you could zoom out angle C. It's an inscribed angle to arc BD. 2 times 20 gives you that same measurement of 40. All right, so keep consulting your green reference sheet. Everything we just talked about in these notes are in here. So we have now kind of discussed all these. Inscribed angles from a semicircle or a diameter, you get 90 degrees. So you get 90 degrees right here. If you have inscribed angles from the same arcs, you get congruent angles. So angle B zooms out to arc AC. Angle D zooms out to the same arc. Those angles are congruent. If you have a tangent to a radius or diameter, you are going to get a 90-degree angle measure. The angle formed from a tangent and a chord acts like an inscribed angle. It's going to be half the arc. Half of this arc. That angle's half the arc. And if you have parallel lines, you get congruent arcs. So if these lines are parallel, you get congruent arcs. So everything we've been discussing is all on this reference sheet. So we have now discussed everything, all the relationships between angles and arcs. You need to know them all. Hopefully they make sense to your brain, so there's little to memorize and there's just a lot to understand. And that is all that we have talked about. All right, you guys have a great day and have fun. Bye.